Thank you for inviting me here. I'm Artur Chmielewski. I'm the US Project Manager of the Rosetta Mission. There's also a project manager on the European Space Agency ESA side. It's an international mission. So today I want to tell you about the mission a little bit, but mostly I want to concentrate on the landing because there are a lot of interesting things that went on this mission from the perspective of engineers. And most of you, I would guess, are engineers here in this audience, just like me. By profession, I'm an engineer. So let me jump into, but let me go back and see if we can make this now. Okay, so let's start with comets. So when we say comet, people envision something like this, right? There's this big, bright, white tail in the sky. And they say, oh, here's this beautiful comet. But comets, of course, have not only one tail, but most of the time, or all of the time, two tails, and sometimes three tails. And as you can see here, there's the dust tail, which is the very reflective white tail because it consists of dust. And these tiny dust particles act like tiny mirrors and reflect a lot of sunlight. And that's why most of the time we see this beautiful dust tail. But there's also ion tail, and these are ions. And that always, you can tell from this picture where the sun is, because your ion tail will be always on the opposite side of the sun because it's caused by creating ions. The solar wind creates the ions, okay? But what you cannot see ever in the sky and on this picture is the comet nucleus. And that's what's most interesting to the scientists, right? And the reason you cannot see the comet nucleus is because it is for various reasons. It's tiny. It's probably like about 1/10 the size of San Diego. It's about, in this particular case, it's about 2 kilometers by 4 kilometers. And it's also very dark. And I'll tell you in a moment why it is so dark. But it is twice as dark as fresh asphalt. And for that reason, when JPL looks out in the sky and uses, and some surveys look out in the sky to see at the approaching objects who could put a damper on conventions like this, then comets are very much in the forefront of the objects that we're looking for, because not only because they are so dark, they travel with huge speeds, but they have a tendency to change their trajectories. So they are even more dangerous than asteroids, which are more predictable, or chunks of asteroids. But believe me, I don't know if you can see it, but the comet that we're going to be talking about, Churyumov-Gerasimenko, is there. Okay, and it is the albedo of these objects is to scale here. Okay. So why are we interested in comets? Why is NASA and the scientific community interested in comets? So I'll jump into this by showing you in a minute a short movie that represents the NICE model. And so you folks, you have a lot of breakthroughs. So make sure you're not going to make the same mistake that the scientists made here. You know, they developed the model by going to Nice, France, okay? And there are some problems with this, right? Because they had a breakthrough, and from now on, they kind of like appear like guys go to a nice resort town in Europe to talk about science. Well, that doesn't really look good, first of all. Secondly, if you're going to pick a city, don't pick it with a name like Nice, because a lot of people, the general public, will say, oh, it's a nice model. Well, the model is very nice, but so, use a little more political, better perspective when you're going to be going for your meetings, okay? San Diego is okay, I guess. Okay, so let's look at the NICE model, and there are some others. Okay, so it all started 4.6 billion years ago, right? And there was gas, there were a lot of elements floating in a cloud, and possibly a nearby star came by, started spinning motion of this gas, you started creating an accretion disk, and pretty soon the sun formed. Of course, sun, due to gravitational collapse, lit up. Pretty soon you have these clumps of matter forming bigger clumps. Now you form planetesimals, you have collisions, and pretty soon, these bigger planets start forming, right? And we've all heard about it. We've seen these simulations, this one and others. We can see how Earth formed eventually, and it all happened in the first roughly 50 million years of the 4.6 billion years ago. But look at what's interesting here is look at the violet stuff on the outskirts, right? This is the interesting stuff. This is where the comets formed. Because the reason it's interesting is because if we try to figure out, the NICE model and a lot of these models, they work very well, like very good computer simulations. The only thing that is a problem is that we don't exactly know what were the very first inputs into this. T equals 0. What are these very early particles that we should start our simulation with, right? And the reason it's so difficult to figure out, for example, on Earth, is because no matter how deep we dig under this convention center, it's all processed material, right? Volcanism, life, decomposition, tectonic movements, all of that process this material for billions of years. And it's very difficult to figure out, go back in time and figure out what was this original material, right? So now I'll play it again. So what is interesting about comets is that comets formed on the suburbs far away from the sun. When you see again this violet kind of, we designated it with this violet color, this material. So it's pristine, it's frozen, it's all preserved for us. If we can just get to it, we'll know what this material was. What were the early molecules that formed the solar system? And that's what scientists are really excited about. There are some other reasons why comets are interesting. A lot of scientists believe that comet brought water to Earth. So those of you who took a shower or bath this week, maybe you showered in comet, okay? But this hypothesis is still tested. But if we could taste the water on a comet, we could see what is the D to H ratio on the comet water and see if this is the same composition, same isotopic composition that is in our oceans. Because a lot of people don't realize, but yes, there was an early water on Earth, but somehow it escaped. The sun was very hot, there was a lot of bombardment that possibly heated up Earth, and all the volatiles escaped. Water escaped. Earth was a very dry planet. But then the water came back. So what brought it back? And a lot of people think that maybe comets. If you have 10,000 comets bombarding Earth in a year, then it's a huge volume of water. And this is something that we're very interested in testing too. Okay, so I'm going to be talking about the mission called Rosetta. And why is it called Rosetta? Well, for the very reason I described. The Rosetta Stone was the one that allowed us to translate hieroglyphics. And the reason it did is because you can see that it has texts, ancient text in 3 languages, hieroglyphics, and then also is Greek and demotic script. And the text was identical. We understood Greek, so now for the first time on this stone we were able to figure out what is the significance of hieroglyphics. So there was this key. And we think that the comets will provide this key to the early solar system. And that's why we named this mission Rosetta, after the Rosetta Stone. So the Europeans built a spacecraft. The US donated 4 instruments to it. It's a very big spacecraft. It's about the size of bigger than the biggest SUV. And we launched it 10 years ago. Besides the instruments, the US provides about 45 scientists. We also do shadow navigation. So we can arrive at 2 independent solutions for the position of the spacecraft with respect to the comet. It's a very difficult, extremely difficult problem. I really, my hat off to the navigators, because to be able to figure out with meter accuracy how far is your spacecraft from this moving comet at a distance of 400 million miles, that's just, to me, it's mind-boggling. But it was done. The spacecraft was also interesting is because this was the spacecraft that was the farthest spacecraft built by us that depended on solar power. The comet that we wanted to explore, Churyumov-Gerasimenko, is on this very elliptical orbit. So we had to build solar arrays that are like the size of a tennis court, because 8 kilowatts on Earth orbit would translate into about 450 watts when we're past the orbit of Jupiter. And that was the trajectory we had to get on to catch up with the comet. And this looked like this. I'm not going to explain this in detail, but the reason it's so convoluted is because we had to do 3 flybys of Earth and 1 flyby of Mars to be able to pick up enough to get enough of the gravity kick to get the kind of speeds that we need to move alongside of the comet and get into this elliptical orbit. And this whole mission took 10 years. We've been at the comet now for a year, so it took us 9 years to fly. On the way we saw 2 asteroids, so there was a bonus. But it's a very difficult mission also because you realize, we service our cars every, 30 hours approximately of driving. Here everything had to work for 9 years, and it did. Most of this stuff. I tell you what didn't work. Because between us engineers, we have to talk about problems, failures. Otherwise, it wouldn't be an interesting talk, would it be? Okay, so comets are named after their discoverers, and in this case, there were two astronomers from Ukraine, Churyumov and Gerasimenko, and these are the original plates from their discovery. Now that's okay, that's not so fascinating. As a matter of fact, that's pretty boring. Now, is this fascinating? Well, to me it is, because this was the best image of Churyumov-Gerasimenko that we had before we launched our spacecraft. And this was, so hopefully all your projects have a little bit better defined requirements. Okay? Because, here we're told, oh, you see these 10 pixels? Go and land there. And what's the environment? What's the temperature, right? What's the shape of this thing? What's the size? What's the rotation? What's the morphology of the surface? What's the surface like? We don't know, but go and land. So that's really amazing. Now, we looked at the Churyumov-Gerasimenko 67P, with Hubble Space Telescope, and we got something a little bit better based on light curve. And I also did 3D printer model of this. So when I talk to the scientists, they can explain to me things that we can maybe plan the surface mapping easier, then we can talk about landing easier when you hold something in your hand, right? And so I was very proud of myself, did this 3D printer model and went to one of the leading scientists and showed it to him, and it kind of looked like deflated soccer ball, you know, something that Ronaldo kicked and punctured from a couple of sides. And I showed it to him, and he says, Art, please put it away. Please don't show it. I know you want to be exciting, you know, you want to probably show it in some TV interview or something, but that's not what it's going to look like. This thing's been around the sun 200 times. It's heavily eroded. You know, you want to get yourself a model, 3D model of this comet? Go buy yourself a basketball at Big 5, paint it black, you got your model. Okay? All right. So I said, okay, well, what do I know about this? Even this is fascinating to me because this is the best picture of Churyumov-Gerasimenko we had when we woke up our spacecraft, and this was like about 6 months before landing. Actually, it's a movie. I'll play it because that really scared us. Look what happens to this dot. So this is our comet. Whoa. I'll play it again. Doesn't seem like much to you, but I'll play it again. Look, it has an outburst. And we were supposed to land at 3.5 AU because we wanted an iceberg. Okay? We wanted something that is completely non-active, because how else you're going to land, right? And here we're at, this picture I think was taken at actually 4 AU, and look at this thing. So we were really worried. But still, you know, you can imagine the lander team, they still didn't get a whole lot of information here. So, you know, when we conduct these missions now we have animations. You can't have, you know, you cannot have a mission without good animation. So the animation was created. And I want to show you how. So this was, we're showing to the world, this is how it's going to work. So here's your orbiter. It's flying over the comet. The comet, look at the comet, it kind of looks like the moon. You know, roundish, flattish, nice. Here's the lander, which is kind of the size of a dishwasher, deploys. And it scoots down on a surface of the comet. The legs deploy. It's nicely pointed down toward the surface. Everything is nice and controlled. Look how it gently descends, yes, and sits down. And then the harpoons there, it's very low gravity situation, so the harpoons fire and hold it down, and then we conduct our science. And, you know, my personal evaluation of the mission is that if we can exceed the excitement of animation, then we have a good mission. But usually it doesn't happen. But at this time it did. And I'll take you for a ride here in a moment. So this is what the comet's supposed to look like, right? This is how we're supposed to descend. And we land on this basketball, right? Everybody's still preparing for landing on the basketball from a nice circular orbit. And then we get the first close-up pictures from our science camera. And everybody goes, you know, everybody now all of a sudden found God. You know? Oh my God, what's going on here? And so, you know, we started mapping it, and I went to my 3D printer again and got this. And one of the scientists looked at it and said, whoa, space duck. And it turned out that this was the most annoying thing that anybody could say to the project scientist because it's stuck, you know. So the project scientists came out, and there was a meeting just like this. There was 250 scientists from all over the world. The project scientist jumped out on the podium and says, ladies and gentlemen, it's not a duck, minor lobe, major lobe, okay? Thank you. And then 2 minutes later, somebody has raised his hand. So we're going to land on the head of the duck? And then it just stuck. So everybody now was talking about the head. You know, people are talking about butt of the duck and head of the duck. At the next meeting, one of the scientists came out, the project scientist came out, and he thought he found a solution to this unacceptable terminology. So he came out with the model, and he says, today we will be talking about our black swan. Somehow he thought that will be more appropriate, black swan versus a duck. But of course, you know what happens, right? A minute later, somebody raises his hand and says, yeah, but wouldn't it be easier to land on the butt of the duck? So it became a duck. But, but this is scary. And the lander team was really worried. And then, of course, we started seeing activity, which came from the neck mainly at that time. And this was also, we started seeing a crack down the neck. I mean, is this going to separate? And I was telling them, don't worry about this. This will be good, because then we have Churyumov and Gerasimenko. But the shape was really difficult for landing. And I'll show you this picture. I showed it only once in a public presentation. And I'm so happy that I have a scientific audience here, because when I showed it, I was trying to visualize, the size of the comet. But everybody went, oh my God! Is this going to land? Is it going to hit us? So I said, no. So this is the second time I'm showing, actually, this picture. Of course, it's with the backdrop of Los Angeles. But the shape was, in a minute, I'll explain to you, was actually worse news than we even initially thought. That even Lulu was worried when I showed her the model. And scientists always tell me that whatever picture I show, I should also have credits always. So I have a credit on this picture too. But then we had to find some landing spots on this. So, and unfortunately, everything was going fast. We had to find a landing spot within days, because the comet is approaching the sun. It's moving very fast, so there's not that much time. So we had to decide on landing spots when we didn't have even high-resolution maps, before we were even in orbit of the comet. So we found 10 spots, then we found 5 spots, and these are the 5 spots. We numbered them, and then we had to go to 3-day meeting with everybody from the whole project, all the scientists, and we had to narrow it down to the best spot and a backup spot, okay? And of course, it's this is where I realized how difficult this landing is going to be, because first of all, you have to be moving exactly at the speed of the duck, right? And the duck is moving 45,000 miles an hour, right? So this is like 15, and later it goes even faster, something like 15 kilometers a second, right? And you have to be 15 kilometers a second plus minus about a meter per second for your spacecraft, right? To be able, the reason I have our landers sitting on the bus, because I'm from Poland. And I was always thinking about it as, so you have to, in this country, actually the drivers have the courtesy to stop at a bus stop. That's not the case in Poland, at least it wasn't when I lived there. And so, so you learn dynamics, space dynamics, because you have to be moving on the same trajectory as the bus. And then you have to acquire the same speed, because he will open the door for you, but, you have to do the jumping, right? And So you have to be the same speed, you have to be at the same trajectory, and that was very tricky, right? And then, you have to avoid boulders on the surface, and it turned out there wasn't an nicely eroded body like the scientists promised to us. There were a lot of huge boulders, and the boulders were like, the size of this room. One scientist told us, oh, but don't worry about the boulders because they're like eggshells, So there's a huge boulder, but it's actually, just thin crust and there's nothing inside. So even if you land on it, it's not going to bother your lander. Well, thank you. Do you want to take that chance, It's like, always assuming on the highway that if you see two lights approaching you, it's two motorcyclists side by side, right? So you stand in the middle. You can't do that. So the boulders, big scarps, you have to avoid this. And, this was the terrain, right? A lot of boulders, a lot of scarps, a lot of crevices. And this is representative of most of the terrain. So this was really dramatic. And these boulders are like, a lot of them are sizes of single-family homes. Also, the lander had to land on a slope that is less than 30 degrees. Otherwise, it would tilt over, okay? Because there is such a low gravity. So we had to find out, we couldn't find a landing ellipse with just flat terrain. So most of it was about 50% steeper than 30 degrees, and and the rest was acceptable for landing. And some of it, so here we found places like this, okay, and I would look at this and say, oh great, here's our landing spot. And then you talk to the scientists and they say, dunes. Dunes. What do you need to get dunes? Wind. There's no wind in vacuum, right? So the hypothesis was that maybe it looks nice and flat, but there's a wind underneath because it's like a cloud of dust, right? So there's a layer of cloud of dust, and then there's wind from all the gas that is sublimating underneath, swooshing around, okay? So do you want to land on this? So this is even more scary. So activity, right? I was thinking, okay, well, you have to avoid active areas. It's supposed to be very quiet when we land, but it turned out that it was pretty active. And we started getting these images, and there was a lot of activity. So you have to avoid these jets. Now, later it turned out that these jets, a lot of them come out of these, I don't know if you can see, I don't have a pointer, but you can see the round kind of silos. This is where the jets were shooting out. And later when we got some close-ups, they were really very smooth, round silos. And maybe we can talk about it some other time, but there's a very interesting physics that creates them. But of course, you have to avoid them. You can't, land on the edge. And then, of course, the lander had a primary battery. So could work for about 2 days on the primary battery. If you want to do more science on a surface, you would have to recharge the secondary battery, right? So you would have to get 6 hours of sun a day. And the comet spins every 12 hours, okay? So you have to also figure out where are these spots, right? So now we started making these maps of with respect to illumination, with the trajectories, which spots are flatter, where there's this 30 degrees, and finally we converged on our landing spot, which turned out, like the first scientist noticed, was on the head of the duck, right here, right above this nice flat area, which was later dismissed when we got better pictures, because it turned out it had 358 boulders of the size of a single family house. Okay, so it was eliminated, but we landed on the tip of head of the duck. Okay, and this was the landing site that was selected, and you can see this is not perfect. Okay, a lot of areas there that where you, and we can't control. This is a ballistic landing. It's not like Curiosity. You can't aim for a spot. You can't make any adjustments. Once you release, oh, okay, thank you. Once you release your lander, you don't control it, right? So, so that was very exciting. The whole release to landing is 7 hours because the speed with which the lander descended was about like this. 7 hours, about 22 kilometers. Okay, and so you can imagine what was going on through our heads during the descent. Okay, and then we released the lander, and then we got a first picture from the science camera, and you can see what's here in this circle. There's a little dot descending. Everybody was so thrilled, yes, because this was the first image where you could see actually what's going on with the lander. And here's, of course, the comet, okay, the comet nucleus. So, and then, of course, our whizzes, digital whizzes, took a close-up of it, you know, enlarged it and processed it, and here's our lander. And the legs were pointed down, you know, as they supposed to be, was slightly spinning, so everybody was really thrilled. And then we started getting the first images. You can see here the leg of the lander, and this is from actually a picture from the science camera. The camera actually had a focal length of 30 centimeters, but a lens would swing in and make it infinity, and that's why we were able to see some things here on the way down. So here's an area which was initially selected as the landing site because it looked so flat, and then we started seeing these boulders, and statistically it turned out to be bad. And the funny thing was actually that one of the reasons this was a scientist's early preferable choice was because somebody called it a heliport. Okay, it was just because of this name. I think it was really difficult to reject it. Well, why don't we land in heliport? Well, the hell part of the port was turned out to be the reason. So we decided to land here, and so it was an ellipse about 1 kilometer size, and uncontrolled. It was so there was not Gaussian distribution. We didn't know exactly where we were going to land. And here's another picture of this area. And here's one of the last pictures before the landing. So you have all these boulders here that are about 1 meter. Here is something huge. So if we land somewhere here, we're dead. We're not sure how much dust it is. You remember moon landings, you know. We still didn't know if the lander is not going to sink. It was a similar thing. But there was a touchdown, and that touchdown was almost exactly at the time when we expected it. So everybody was thrilled, and we got a signal with 28-minute delay because it was roughly about 380 million miles from us. And you know, and you saw these pictures, and all the press and cameramen started taking pictures of operators jumping and hugging, right? But if you look at these pictures, there's a guy that's still looking at the monitor there in the back, and he doesn't look happy. And the reason they didn't look happy is because of this. Okay, the lander was supposed to land, and there are 7 cameras that's supposed to return panoramic, right? But this is what we got. So what the heck is it, right? Something is strange. And then, next time the cameras turned on, we got this. Okay? Now, this is a super exciting picture, and there's a lot of science in it. You can see the leg of the lander here. So this is underneath the lander, and there's no dust there. There's a lot of cracks. Is it is it an icy material? What is it? It was very surprising. And then we started getting more pictures, especially from the science camera. And then we started putting it all together of what happened. And it was really exciting. You can see here, so here's our lander, right? And this is a blown up picture, a large picture here. And here it's landing, right? So it's on the way to the landing site. So it lands here, right? And we know that it landed here because it kicked up some dust. So it actually landed right before this humongous rock that I showed you before, right? But then what happened, because it's such a low gravity situation, we're supposed to fire harpoons underneath, right? Because here the gravity brings it down, but on a comet, this thing, even though it weighs as much as a refrigerator, it, on the surface of the comet, weighs as much as a penny. So it would bounce back, so the harpoons fired were supposed to fire, and as a jet on the top, they're supposed to press it, to prevent it from recoil. And neither one of them worked. Okay? So what happened is that the lander bounced and started traveling sideways. And you can see it here. Right? And what it did, amazingly enough, it was like it joysticked itself, because it was flying just high enough to clear all these 358 boulders that were the size of a house. So it was just high enough, about 100 meters, and it flew over them. And then a terrible thing would have happened, because it would have gone into the orbit of the duck, but it hit a hill, and a hill absorbed its energy, and it tumbled a few times. And so this was the landing site where it's supposed to land, and it did land here, almost in the middle of this ellipsis. And it flew right over the heliport and hit this mountain range, and it tumbled and fell into a crevice like a golf ball. Okay? And then, unfortunately, it got stuck in almost vertical position like this. So that's why this picture showed the sky, one leg and a sky. And it also showed a wall. So a couple of the experiments didn't work, and unfortunately the drill didn't work. Unfortunately, the chipper didn't work. But some scientists were extremely happy with this, because instead of getting one measurement, like for example magnetometer people, getting one measurement in one spot, they got a series of measurements over a kilometer. So they were thrilled about it. And so I see that my time is almost up, so let me conclude this. We're still getting amazing pictures. There's amazing science coming from the mission. Next week is the perihelion, so the closest approach to the sun. So that's very exciting to the scientists, because it will be almost maximum activity. Unfortunately, we have to move the spacecraft away from the comet because it's so active. And we didn't do it as we expected earlier. That may be the case because there may be so many chunks of ice and particles that will impinge on the camera or on the solar rays. We did this because the star trackers are getting confused. Because those of you who build star trackers, you know that it takes the first 2 stars, and then it takes the 3rd one, and then it goes for the 4th one for confirmation of position, and it goes to the database, right, and tries to find itself in space. Well, this is very good, and it uses maybe 5 stars, but what do you do with the other 10,000 shiny particles of dust? Right? So the star tracker is getting really confused, and because of that we have to, and the spacecraft loses control, and that's why we had to move it back. But the science comes in, the science about the water, the science about the organic compounds, magnetization, and especially people who model, you remember my first slides, people who model the early solar system are getting excited about the results. So for the next year or so, you can see here, this is the orbit of the comet, Churyumov-Gerasimenko. This is the orbit of Earth. right? So we were at the closest approach. We landed here where the red dot is, and now we've traveled this this distance here. And we're going to be going, so we started observing it somewhere here, and we want to stop our mission when we get the symmetrical point after the perihelion to be able to compare both legs, before and after perihelion. And just several days ago, the scientists decided how we're going to end the mission, and they chose something that some scientists are not very happy with, but certainly for the PR purposes, that will be exciting, because now we're going to land the orbiter on the comet in September of 2016. So there will be more excitement coming. And we're very happy that ESA and DLR, who build the lander, got all their ducks in a row. And thank you so much for listening.